Hi, in this video I'm going to talk about binary numbers, but the first thing I want to talk about is a bit. And a bit is a number that just has two states. It's a 1 or a 0. It's also the smallest piece of information that a computer or a microcontroller can handle. And if we were to put 8 of these together like this, we get a byte. And a byte in the past has been defined as either 8 bits or 16 bits, but today I think it's commonly accepted as being 8 bits together. And that's how our memory is organized in bytes. Well, depending on the machine that you're working with, they certainly identify how much capacity a memory has by the number of bytes, even though the computer system may be accessing 4 bytes at the same time. For example, in your PC, the Intel CPUs that are in a PC, they are 64 bits, or sorry, not 4 bytes, but 8 bytes in a row, and they'll access 8 bytes all the time. But in an ATmega that's used in the Arduino, everything is done with a byte. It only works with 1 byte at a time. Even though you might be working with a 16-bit number, it works on it as 2 separate bytes. Now we organize our 8 bits into a byte like this, and if we were to work out all the different combinations of 1s and 0s between all 0s and all 1s, we'd find that we'd have 256 different combinations. And so a byte can hold the information of up to 256 different pieces of information. Now, the bits are organized in order. We call the far right bit the least significant bit. It's bit 0, and then bit 1, 2, 3, all the way up to bit 7 here, which is the most significant bit. And these are arranged as powers of 2. Now, in our normal decimal numbering system, we have our digits, and they're organized in powers of 10. So this digit here would be 10 to the 0th power, or just units from 0 through 9. This one here would be the numbers of tens. This would be hundreds, thousands, 10,000, etc., etc. In the binary numbering system, we use powers of 2. So this is the 2 to the 0th power, which is the units digit, same as in our decimal system. This one over here is 2 to the 1st power, which is just 2. And over here is 2 squared, or the numbers of 2 squared, which is 4s. 8, 16, 32, 64, and 128, all the way up to here to bit 7. And so when you have a 1 in one of these digits, that's the number that it represents. So a 1 here and nothing else being 1, all zeros, so a 1 over here would represent 8 in our decimal numbering system. A 1 over here would represent just 1. If you had a 1 and a 1 here, and these two were 0, that would be 8 plus 1 is 9. So this is how you can figure out what a binary number is in decimal. You just add up the number of 1s according to their power of 2. Now, inside the computer system, or the microcontroller, 1s and 0s are represented by voltage levels or by switches, transistors turned on or off. So, for example, a 1 might be represented by a high voltage, and a 0 would be represented by a low voltage. Now, I don't know exactly what's going on inside of, say, the ATmega, what the different voltage levels are inside on the chip itself, but on the I/O pins, a 1 is represented by a high voltage, and if you're running your microcontroller on 5 volts, it's generally a voltage higher than 3 volts on a pin would represent a 1. And a 0 would be represented by a voltage below about 1.5 volts. And you'll notice that there's a gap between 3 and 1.5 volts where there's no logic level defined. So you must get the pin below 1.5 volts to get it to read a 0, or get it higher than 3 volts to get it to read a 1, or whatever it might be. That voltage level will be different if you're running the microcontroller on 3.3 volts. Or other microcontrollers that operate off of different voltages. Some microcontrollers run at 1.8 volts or 2.7 volts. And so their 1s and 0 voltage levels will be a little different. But what goes on inside the chip, the voltage levels are probably defined by the chip manufacturer, but we don't have to worry about those because it's all taken care of inside. It's just the I/O pins when we're working with them. Now, if we were going to work with more than 8 bits, more than a byte, say we go to 16 bits, for every bit that we add here on the end, we simply double the number of combinations. So like I said, with 8 bits, we have 256 different combinations. So I can store, like I said before, data for up to 256 different items in a byte. If I went to 16 bits, that would be 65,536 different combinations of 1s and 0s between all 0s and all 1s. And so with a byte, or with 16 bits, we can store a lot more information. In previous tutorials, I've talked about choosing data types for your variables to be big enough to store the number that you're going to end up with when you do your calculations. So a byte, actually that's one of the data types, is a byte. Char, C-H-A-R, is another type, still a byte. If you define an int, that is 16 bits. And a long is 32 bits, 4 bytes together. So with a long, that's 2 to the 32 power, 2 to the 32nd power, and that is quite a large number. You can go work it out on your calculator. I think it's like 4 billion or something like that. I forget what it is. But it's a large number. So with 4 bytes or long, you can store some very large pieces of data in there. So when you're writing your software, just understand what a byte is, how many bits it is, or what an int is, or what a long is, the number of bits. The more bits you have, the more different types of numbers you can store in that. Now, if I was going to write down a binary number in the notation that the compiler understands, I would write it down as, you start off with a 0b, and the b can be upper or lowercase, it doesn't matter. And then write down what bits you want all the way down to, well, the total number of bits that you want to put in there. If I'm setting up a register in the microcontroller, most registers are 8 bits long, I would just write down the 8 digits, or the 8 bits. Or whatever, 1s and 0s here, depending on what bit I want set or cleared in that register. And I always write down all 8 of them. You can get away with not writing all 8, but what the compiler does is it assumes that the last one here is always the units digit, and it just sets to 0 any of the ones that you haven't defined here. So if I was just to put down 0b with just 4, whatever these combinations of 4 bits would be written to the lower 4 bits of the register, and the upper 4 bits would just be written 0. But just to avoid any ambiguity, I suggest that you write down all of the bits when you want to set up a byte, or a 16-bit register. You can do it the same way, you just put down 16 bits as well. It gets a bit cumbersome, obviously, the bigger the number that you're writing there. So that's how you do it in the compiler. I'm going to show you another type of notation called hexadecimal. So with hexadecimal, I'll just do it with a byte since it's easier to work with. We write down all of our bits, but then we divide them in half into 2 chunks. So each half here has 4 bits, and there's a total of 16 different combinations. 2 to the 4th power, or 0, yeah, 2 to the 4th power is 16. So there's 16 different combinations that we can use, and we'll denote them with our decimal numbers, so we can go from 0 to 9, for the first 10, but we have 6 more left over. So how do we represent those upper 6 digits for the hexadecimal number? Well, we represent them with A, B, through to F. And it could be upper and lower case as well. So our hexadecimal numbering system goes from 0 to F. And we denote them with 2 hexadecimal digits for a byte. So this digit would be the first 4 bits, or the first upper bits of the byte would be represented by the first digit, and then the next digit would represent the lower 4 bytes. So since I've written zeros there, our hexadecimal designation for this would be 0, 0. And the way you write that in your compiler is you write 0, X, kind of like what I did before for binary, except it's an X here instead of a B. That X could be uppercase or lowercase. And then you follow it by the number of hexadecimal digits that you're interested in. And in the case of a 8-bit number, it would be just 2 hexadecimal digits. So it could be 1C. And that would look like a 1 in the upper one, so 0, 0, 0, 1. And in the lower one would be a C, which is 1, 1, 0, 0. C corresponds to decimal 12 in base 10. So it's 1. Remember, from the previous sheet here, I showed you, we'll just look at these ones here. So we've got groups of 8, 4, 2, and 1. So if we were to look at what we've got here for a C, we've got a group of 8 and a 4. So we add 8 and 4, and that gives us 12. So that's how you can figure out your hexadecimal number as well. So that's an easier way to write down your ones and zeros. Instead of doing it in binary, which you need to have 1 digit for every bit that you're going to set. Here you only need a digit for every group of 4. And so if you were talking about a 16-bit number, your hexadecimal notation would just have 2 more digits here. Instead of just 1C, it could be 1C00 or whatever. So that's hexadecimal notation. There's another method of grouping these bits into groups of 4 again, and we call that the binary coded decimal, B, C, D. And it's useful because it kind of mimics our decimal numbering system. And in this case, we divide our binary number up into groups of 4. But what we do is we constrain each of these groups of 4 into the range of 0 to 9 only. We don't have combinations for anything above 9. And so we could have a binary coded decimal here of 1, 4. And that would actually mean 14 in our decimal numbering system. So it would look like 0, 0, 0, 1, and a 4, which would be 0, 1, 0, 0. But remember, the difference between these two is that we only allow a combination of 10 different combinations here for each of these 4 bits instead of 16. There is no notation for that, no special 0x kind of notation. What you could do is, if I wanted to represent this number in the notation for the compiler, I would simply write it out as the digits. So 0x, just like in hexadecimal, but I just write 1, 4. So no A, B's, or C's, or D's, E's, or F's will show up in here. And that will give you the same thing as a binary coded decimal. Now, we can perform the normal arithmetic operations on binary numbers, just as we do with decimal numbers, adding, subtracting, multiplying, dividing. And the rules are the same. And what I'll do is I'll just choose 2 decimal numbers here, 74 and 67, convert them into their binary equivalents, which I've done here, and then I'll add them just the way we would add decimal numbers together. So if you were to add 4 and 7, you would get 13. Or not 13. 4 and 7 is 11, sorry. Not thinking straight here. So 11. You can't put 11 in this one little spot here, so you have to carry the 1. So 8 and 6 is 14. 141. So we'll apply the same rules to the binary numbers here. So 0 plus 1 is 1. But here's an issue. 1 plus 1 is, well, 2 doesn't exist in here, so we can't put 2 in there. Remember, a 2 is a 1, 0. So it's kind of like a 10. So what we do is 1 plus 1 is 0. Carry the 1. And then we, same as we did over here. Then we continue on. 1 plus 0 is 1. 1 plus 1, or 1 plus 0 is 1. 0 plus 0, 0 plus 0, so we get zeros there. And then we do the same thing again. 1 plus 1 is 0, carry the 1. 1 plus 1, or 1 plus 0 is 1. So our answer is 1, 0, 0, 0, 1, 1, 0, 1. And when you convert that from binary into decimal, that's what you'll get, 141. Let's say we want to do a subtraction, 74 minus 67. So I'll put down the binary equivalent of 74 here. Actually, let's go back up to this one. So we can brute force our subtraction here by doing it the way we would do in decimal. So 4 minus 7, well, we can't do that because 4 is smaller than 7, so we have to borrow. So we borrow 1 from the 7 over here. That becomes 6. That becomes 14. 14 minus 7 is now 7. And then 6 minus 6 is 0. So our answer, 74 minus 67, is 7. So we can do that over here as well. 0 minus 1, well, we can't do that because same reason as in the decimal here, so we have to borrow. So we make that a 0, and this is a 1, 0 now. So 1, 0 minus 1, or 2 minus 1, is 1. And we can go on and do that, and we'll come up with the same answer as I did here with the subtraction. But I'm going to show another way. In fact, this is the way that the computer actually does it. And what subtraction is, 74 minus 67, is the same as 74 plus minus 67. So I'm going to show how to make this number here a minus number. And we'll do it by what's called a 2's complement. And a 2's complement takes 2 steps. The first step is to convert all the digits, one at a time, into their other digit. So a 0 becomes a 1 becomes a 0. And you do that all the way through until you have the complement of this number. This is the number we're going to make negative. And then when you've done that, you add 1 to that. And that will give you the 2's complement. So let's look at it down here. So this becomes 1, 0, and then a whole bunch of 1s here. And then a 0. Now the last one is a 0, but since we add 1 to make the 2's complement, I'll add 1 there. And then we simply add them. Same thing as before, taking the negative of this number and adding it to it, the same as the subtraction. So we do the addition. So we've got 1, 1, 1. Now here's where the fun starts. 1 and 1 is 0, carry the 1. 1 and 0 and 1 is 0, carry the 1. 1 and 0 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. Now, we're only going to work with 8 bits, so we can ignore that carry. And what did we get here as the result? Well, 1 plus 2 plus 4. So that's 1 plus 2 is 3 plus 4 is 7. So we got our answer of 7, just as I did before. So let's write it down here. 74, 67 equals 7 with the subtraction. So that's what a 2's complement does. You complement all the bits. That means you turn the 1s into 0s and the 0s into 1s. And when you've done that, you add 1 to that. and you add 1 in the normal way. So if our 2's complement happened to be, say there was a 0 here, so our last bit would have been a 1, and we added 1 to it. So 1 and 1 is 0, carry the 1, and you'd have to do that same addition all the way through and carry that 1 all the way through. So this is the representation of a negative number. And you'll notice how in the upper bit here, the sign is a 0 here, or sign, sorry, that's the sign bit. I'm jumping ahead of myself here. The upper bit here is called the sign bit when you're treating this as a signed number. And when the bit is 0, it's a positive, and when the bit is a 1, it's a negative. So in your C code, if you declared a variable as a char or an int, the compiler treats it as a signed number. And it looks at the upper bit and treats it as a signed number. If it's a 0, it's a positive number. If the upper bit is a 1, it's a negative number. And so you've got to watch that. Sometimes you might get some weird results when you are treating it as an unsigned number and you're starting to do math with it. It might come out with a weird answer. If you want to work with only unsigned numbers, then you've got to declare those variables, char and int, with the another word. You write down unsigned char and unsigned int, and that treats them as unsigned numbers. So a char, an unsigned char, can take on the values of 0 to 255. There's 256 different combinations, just like I described earlier. If it's a signed char, just a char, it can take on a range of numbers of minus 128 to plus 127. And if you work that out, you'll still see you'll see that there's still 256 different combinations, from minus 128 through 0 to plus 127. And like I said, you've got to be careful when you're playing with these numbers. If you don't declare them as unsigned and you're expecting them to be unsigned, you might have some weird results. So let's look at signed numbers. I'm going to look at signed numbers a little bit later. Let's look at multiplication and division. So multiplication is kind of like shifting these numbers back and forth. So if I were to shift my numbers this way, so for example, take this bit here, move it over into that bit, and that bit over to there, and so on to the right, so I'll end up with a number that looks like this. I'll shift it one bit to the right, and we'll just shift in a 0 into this left-hand one, so 0. So it's going to look like 0, 1, 0, 0, 1, 0, 1. And the last bit here got shifted off and dropped off into space and disappeared. It's lost. So what I've done here is I've shifted the bits one decimal or one place to the right. And that's the same as dividing by 2. So if we work this number out, it becomes 1 plus 1, 2, 3, 4. 1, 2, 3, 4. Did I do this right? 1 and 4, 8, 16, 32. Yeah, it'll work out. 32 and 4 is 36, 37. So that's 37 decimal. 74 divided by 2 is 37. If I were to take 67, for example, and shift it to the right, shift all the bits this way, so that this bit here drops off into space and is lost, and we'll shift a 0 into this location here as we shift it over. So I'll ignore that one and I'll write it down. 1, 0. Well, let's see, there's 4 zeros there in order, followed by 2 1s, and then we've shifted in a 0 into this. So we've shifted, the upper one was shifted to the right, we're shifting the left one, or the lower one to the left. Well, that's the same as multiplying by 2. So if we work out what this number is in decimal, it's 2, 4, and 128, so 134. 1, 3, 4. in decimal. So 67 doubled. 2 times 7 is 14. 2 times 6 is 12, and 1 is 13. So 134. So shifting left by one position is a divide or a multiply by 2. And for every shift to the left, that's another multiply by 2. So if I were to have shifted this number here left to 2 bits, that would have been like multiplying the number by 4. And the same is true going the other way. If I'd shifted this 2 bits to the right, that would have been like dividing it by 4. Of course, there are functions in the compiler. Well, actually, there's not even functions. The compiler just recognizes the normal operators, plus, minus, times, which is an asterisk, and divide, which is the slash. So the compiler recognizes these and automatically creates the assembly language code, or the native code, to do these adding and subtracting and multiplying and dividing. And if you have a chance to look at the assembly listings of your compiled output, you might see how it actually does your multiplication or your division. Of course, multiplying by 3 and not by 2 is a little more complicated, but it might do something like shifting left by 1, which is a multiply by 2, and then just adding another one of the original number back in, and that would be the same as multiplying by 3. There are other kind of shortcuts ways of doing it. The normal long multiplication method that we use, where you put the two numbers one under the other like this, and then you multiply a digit at a time, and you put down the answers, and you get this big long column of additions that you do. The compiler may do something like that as well. There are various tricky methods that the compiler comes up with for multiplying numbers other than just by powers of 2, and same with dividing. But it's automatically done for you. If you put these operators in, the compiler knows what you're trying to do, and it writes the appropriate code for that. Well, let's look at signed numbers here. So we'll look at a car. It's a byte. It's easier to work with than an int, which is 16 bits. So car is automatically signed. So therefore it has a range of a minus 128 to plus 127. And remember, I talked earlier about the sign bit, the upper bit. When it's a 1, that means the number is negative. When it's a 0, the number is positive. So let's look at 128, and I'm going to make it into minus 128. So we'll do the 2's complement method. So there's 128 positive in an unsigned byte or car. This is no longer the signed bit, it's just one of the bits in the number. So we'll do the 2's complement. So what we'll do is we'll take the complement of everything, so it becomes 0 and a whole bunch of 1's here. And then we add 1 to that. So 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And it just keeps on going because we're always carrying the 1 all the way through. Oops, I'm getting a bit crowded here. Carry the 1, and we got the 1, we carry it, 1 and 1 is 0, and you got a 1 there. So that's how we came up with minus 128 looks like plus 128 in the signed and unsigned versions. Let's look at 127. So it is 1 less than 128. So it will be 0, 1, 2, 3, 1, 2, 3, 4. So that's 127 plus 127, or just 127 unsigned. So we'll do the 2's complement again. So we get a 1 followed by a whole bunch of zeros. And then we add the 1. And it doesn't change anything except just puts a 1 at the very end here, so that makes it a lot easier to work with. So that's the same as minus 127. Minus 126, you'll just put a 1 in here and a 0 there. So minus 126 will be 1, because of the sign bit here, followed by a bunch of zeros and a 1, 0. And you can work it out all you want. And you keep going down and down and down until we get to 0. 0 is always 0. So there's no signed 0 in this case. So 0 is just all zeros. So a plus 1 is 0, 0, 0, just like the normal binary 1. And 2, etc., 3, so on and so forth, all the way up to plus 127. So plus 127 is going to look like what we had up here, 127. 0, 1, 2, 3, 1, 2, 3, 4. So that's plus 127 in a signed number. That bit is 0, indicating that it's positive. It still uses all the same combinations of the 1s and 0s as the unsigned version, but they have a slightly different meaning. And this works for more bits than just 8. If you have an int which is 16 bits, the same thing works. The upper bit, the most upper bit. So if this was a 16-bit number, there'd be 8 more here. That bit there is still the signed bit, even though with 8 bits it's the one down here. So it's always the leftmost bit of any binary, or any binary number is called the signed bit in signed numbers. And you have to realize that if you are using signed numbers and you're trying to do unsigned calculations, and you're expecting that all 1s, for example, what would all 1s be? See, in an unsigned number, it would be 255, but all 1s would be a different number. Let's see what it is. So to I've got 1, 2, 3, 4, 5, 6, 7, 8. So all 1s. This is a negative number. We've got a minus. We've got a 1 here, so that becomes a negative number. If we apply the 2's complement to it, what does it actually look like? So 2's complement would be all 0s plus 1. So we get, and that is, so all 1s represents minus 1. We've got a 1 there, so that's positive. This is the positive 1. And that's the minus 1. So that is how the signed variables work, signed numbers work. You might hear a term called sign extend. So for example, this is where you might run into trouble actually. It's is when you are casting a smaller variable into a bigger variable. And if you're casting an unsigned car, oops, can't spell here. You're casting an unsigned car to an unsigned int. So if, for example, my unsigned car had a 1-bit here, and I was going to convert that into an int, it's going to look like a bunch of zeros here. So we're going to take the 1, 0, 0, 0, 0, 0, 0. We're going to cast it to 16 bits. It's going to add another 8 bits. And the 1's going to go in there. And 2, 3, 4. So that's the cast of an unsigned car to an unsigned int. But if this was a signed car and this was a signed int, you have to watch out what's going to happen. So if we have under the signed, or just basic car and basic int, so you're taking this number here, it's a signed number now, so this bit here has a special meaning. When it gets cast to an int of 16 bits, it's going to project that 1 all the way through there in order to get it to there. So it's going to look like this. And then your number, the original number. So this is where you're going to have trouble if you're not watching your signed and unsigned characters, or unsigned and unsigned ints, or signed and unsigned longs is when you're casting from one to the other. You have to watch that. It doesn't matter, it doesn't cause problems if your original number is a positive number, it'll come out as positive, but it'll come out as this. But if the compiler is treating these numbers as signed, it's going to sign extend this 1, which is what it did here. It copied the sign all the way across to this bit here. That's called sign extended. So you need to watch that. So just be careful when you're declaring your variables. Be aware of how you're going to use them. And if you're getting weird results because you're casting a small number into a bigger number, then you need to look at whether you're playing with signed variables or not. Now I want to look at some logical operations on binary numbers. So we looked at one already called the complement, or the 2's complement, but the complement is going to apply to one bit, or it can apply to many bits. And the complement is very simple. You just take a 1 and you convert it to a 0, or 0 becomes a 1. And you just do that to all the different bits in the number. Let's look at logical AND. And so that's like adding, or it's an operation on 2 bits. So if you have, well, I think what I'll do is I'll write out a truth table here. We'll have the 2 inputs, A and B, and then our output, we'll call it Y. And our truth table is going to look like this. This is probably the easiest way to look at it. So I'll just fill it in here like this. Now I'm going to take these 2 bits and I'm going to do the AND operation between the 2 bits. So if I go A and B, the result is 0. If I, that's 0 and 0, the result is 0. If I AND 0 and 1, I still get a 0. If I AND a 1 and a 0, it's the same as this one here, I still get a 0. But then if I AND a 1 and a 1 together, I get a 1. So what it means is that if there's any 0 in there, the answer becomes a 0. The operation is a 0. And you can do this to 1 bit, like I've just done there, or you can do it to many bits in a number. And I'll show you how to use that later. So that's the AND operation. Let's look at the OR operation. We'll do the same thing. I'll create a truth table. Fill it in the same way. And in this case, if we OR 0 and 0, we get 0. But if we OR 0 and 1, we get a 1. Or if we OR 1 and a 0, we also get a 1. And if we OR 1 and a 1, we get a 1. So you can see how different these 2 operations are. So if you AND anything with a 0, the result is a 0. If you OR anything with a 1, you get a 1. So ORing a 0 with a 1, you get a 1. Or ORing a 1 with a 1, you get a 1. And here, ANDing a 0 with the 1, you get a 0. Or a 0 and a 0, you get a 0. And the only time you get a 1 out of here is when they're both 1s. So that's AND or OR. Now those can be useful if you want to change a bit, a single bit in a byte. So if I want to make a certain bit in a byte into a 0, I will AND it with something. So if I'll take a number here, I'll just arbitrarily create a binary number here. And say I want to make this bit here a 0. But I want to preserve all the other bits. I don't want to change them, but I'm going to do it with an AND operation. So what I need to do is, looking back at my truth table, I want to make that a 0. So I know that if I AND it with a 0, I will get a 0 out. But I don't want to change any of these here. So what I can do is AND them with 1s, and what will happen to them is nothing will change. You get what you had up here out again. So that's how I was able to change one bit. And I can do that with more than one bit too. I could just put zeros wherever I want the bits to become a 0. If I want to do it the other way around, I want to change, I'll use the same number here. And I want to set one of these particular bits. Let's look at this one here. I want to make that bit a 1. Again, I can use the OR operation here with 1, because we know that when we OR 1 with anything, we get a 1 back. So we know that that's going to be a 1. And I don't want to change any of these ones, just like I did over here. So I know that when I OR with a 0, we get the original number back. So we OR with a 0 here, we got a 0 back. We OR with a 0 here, we got a 1 back. So I just fill the rest of these with zeros. And what do I get? I get the original number back. So that's how I was able to set this one bit. Again, you can do it with more than one bit. You just put a 1 wherever the bit you want to be set. So these are useful operations for setting or clearing particular bits in a byte or an int, 2 bytes or whatever. Very useful when you are setting or clearing bits in a control register within the microcontroller. If you remember my tutorial on the control of the I/O bits by directly accessing the I/O ports, those are 8-bit ports. Each bit represents one of the pins on the microprocessor. If I wanted to set a particular pin on the microprocessor, I just OR it with this number here, with the 1 bit wherever I want to set that particular I/O pin high. Or if I want to clear that I/O pin, make it low, I AND it with this number here, and making the 0 in the bit that I want to make low. There's another operator. It's called exclusive OR, and I can't remember. There's a symbol for it. I'm not sure if there's a like that. I'll have to look it up. But it looks like this with the truth table. So again, I'll just fill it in. And it looks kind of like OR, except that when you've got this thing the same, these two are the same, you get nothing out. So the same with here. These two are the same, you get nothing out. But when they're different, you get a 1. So that's the exclusive OR. Very similar to this one, except for the last place here, it becomes a 0 instead of a 1. And that's very useful if you want to toggle a bit. So to toggle a bit, you simply exclusive OR it with. So if I wanted to change, I want to just simply toggle one of these bits. I'll go back to my same number. 1, 1, 0, 1, 0, 1, 0. And I wanted to change the state of this bit here. I just exclusive OR it. So I'm going to make it a little clearer here. And then I think it's XOR is what you can do. So anyways, I want to toggle this bit, so I make them all zeros, except for this one. And so 0 and 0 gets a 0. A 1 and a 0 gets a 1. So these are going to be preserved. And then the 1 and a 0 get you a 1. And a 0 and a 0 gets you 0. So we noticed that this one here got toggled. If I were to use the same number down here and do the exclusive OR operation again, so a 0 and a 0 gives me a 0. A 1 and a 0 gets me a 1. A 0 and a 0 gets me a 0. A 1 and a 0 gets me a 1. So remember, when they're different, you get a 1. When they're the same, you get a 0. Different is a 1, different is a 1, and the same is a 0. So now I've toggled that bit again. by just simply exclusive ORing the bit that I want to toggle with a 1. Might be useful if you want to flash an LED on an I/O port without having to do any testing to see if the bit's on or off. So you simply exclusive OR it with a 1 for that particular bit. So I want to say my LED was connected to this pin here, and I want to make it go high and low every time I write something to it. So I just exclusive OR this number with the I/O port, and that will cause, every time I do this, every operation, that pin will toggle. It'll cause the LED to flash on and off. Another way of doing it is more complicated. I could look at that bit, and then if it's a 0, write a 1 to it. If it's a 1, write a 0 to it. But that takes more code to do that. And instead of just simply exclusive ORing it. The symbols used in code in the software for ANDing is the ampersand. I'm not very good at writing the ampersand here. How does it actually look? I can't write it out properly. You look it on your keyboard, it's called the ampersand. It looks like the AND sign. The OR is simply a vertical line. And the exclusive OR is the little caret top. And that's how you do it. So it's an operator, it's like a plus or a minus, it fits in between two numbers. So in your, say it's you wanted to toggle the I/O pin here, so you could go port D, exclusive OR equals, whatever we got here, 0B 00010000, and that is doing the same thing as here. You could do that with this one here. We could go port D or equals, and then the same number, 001. Oops, put the 0B in front. 0, 1, 2, 3, 4. So that's how you do it in your software. And then same thing with the ampersand, which I can't write obviously. So that's some basic logic operators on binary numbers. Now you can combine operations that I just talked about to extract parts of a byte. I briefly talked about the shift operations as being a multiply and divide. Left shifting by 1 bit multiplies by 2. Right shifting by 1 bit multiplies or divides by 2. But let's, for example, I've got a byte here that contains 2 binary coded decimals, 2 and a 4, like this. And I want to have access to this one and treat it as a variable 2 all by itself. So what I can do is I simply right shift it by 4 bits. So when I shift it over 4, it'll end up in a lower part of this byte. And the right shift operator is simply 2 of these triangular brackets pointing to the right, and then you put the number in there. So if this was in a variable called, I don't know, VAL, so we could just go VAL equals VAL right shift 4. And so when we do that, it's going to look like this. Remember when I said it shifted? It's going to shift in zeros into this side, and whatever is out here is going to get shifted off the end and lost. So after 4 shifts, you're going to end up with these 4 bits in here, 0, 0, 1, 0, and zeros all in here. So you're left with 0, 2. So now I can play with the 4 or the 2. If I wanted just this one here by itself, I can AND it with another number to clear these 4 bits here. And so I could use val equals val, and I'm going to just draw an AND like that. Ampersands are a problem for me. And we'll AND it with a number that has all of these bits here is 0, because remember, when you AND 0 with something, you get 0. And over here I want to keep this, so I AND it with all 1s. So when you AND it with 1s, you'll keep what you have. So we'll make it a hexadecimal. We can do it binary. So remember our binary notation, 0b. So I want to make the upper 4 bits go away to 0, so I'll make them all 0s. And then the lower 4 I want to keep, so I put 4 1s in there. And so what that will do is we'll produce something that looks like this. This will all go to 0, and this one will be preserved. So you're left with the 4. So that's a way of combining, or actually using these different functions, or these different logical operators to access different parts of a byte. And the same thing can be done with an int with 2 bytes. You just use bigger numbers, or you shift more. If I wanted to put, say I was building a 2-digit binary coded decimal, I wanted to store it in a value, or in a variable. So I want to put a 2 into the upper one, so I can right shift it to the left. So what I can do is our variable that we're going to end up with the binary coded decimal into, I'll do it before. I'll just go through this using val again. So first of all, I want to make val 0. I want to clear it out, and then we're going to put val the 2 in val, which is going to end up in here in the lower part of val. So val is assigned the value of 2. And so what happens, val is going to first of all look like this after that operation. Now we make val equal to 2, so it's going to look like this. Like that. But we want this up here. So I'll just left shift it. Val equals val left shift by 4. And so what's going to happen is when we shift these bits over to the left, zeros are going to get shifted in. Anything that's up in here that gets shifted off the end is lost. So we're going to end up with these 4 bits up here. Zero, zero, zero. If I want to put the 4 down in here, I could do it by simply adding. So I can add 4 to it. Val equals val plus 4. So it'll look like this. And we add them up. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 0, 0. Oops, that's supposed to be a 0, not a 1. 0 plus 0 is 0. 1 plus 0 is 1. 0 and 0. So we've now got our original binary coded decimal of 2, 4. There's another way of putting it in there. I can OR it in. So let's start with the same one up here. 0, 0, 1, 0, 0, 0, 0, 0. So we can OR in val, oops, not that, val equals val OR. Now we gotta, I'll write it out in hexadecimal here, 0x. Remember, we want to preserve these upper bits here when we do an OR. So we have to make these upper 4 bits 0, and then the lower 4 bits, actually I'll use a binary here instead, and the lower 4 bits will be the number 4 that we want to put in there. So remember, we want to preserve the upper 4 bits, so we put 4 zeros in there, and then we put the 4 down in here. And we perform that OR operation. I'll go through it again. Put the 0, 1, no, that was writing this down wrong. Then we have the 4 here. This should be a 0, not a 1. So we do the OR operation. 0 or 0, 0, 0 or 0. 1 ORed with anything is always a 1. And these are zeros here again. 1 ORed with anything is always a 1. And there we have our 2, 4, and binary coded decimals. So I think that's about it for binary numbers. Let's just do a quick summary because I think I went through quite a bit. I talked about a bit, which is just a 1 or a 0. I talked about putting a bunch of bits together to make a byte, or even more of them to make an int or a long. I talked about the powers of 2, which is exactly the same thing that we do with our decimal system, which are powers of 10. And when you want to add up a binary number to figure out what it is in decimal, wherever there's a 1, you just add in that value of the power of 2. And when you add them all up, you'll get the actual decimal number for that value of the binary number. I talked about dividing the numbers up, or the digits, the bits up into groups of 4 to make hexadecimal. So with 4 bits, you've got a combination of 16 different combinations, and we can name them 0 through 9 plus A through F. And so we get into the hexadecimal or base 16 numbering system. And when you write that down in your for your compiler in your code, you prefix it with a 0x, and then you follow it with the digits in hexadecimal. I also talked about binary coded decimal. That one you have to manufacture. The compiler doesn't do that automatically for you. But what you do is you still divide it up into groups of 4 bits, but you constrain the combinations of the 4 bits to be 0 through 9 only, and the upper 6, A through F, don't occur. Adding and subtracting of binary numbers, it's done exactly the same way we do it in decimal. You add it up a digit at a time, and you just do the carry. We only have 2 digits to play with, a 0 and a 1, and not 0 through 9, so it actually could be simpler. It takes a bit to wrap your head around adding binary numbers together, but it's done the same way, column by column, doing the carry, adding the carry, and etc., etc. And subtracting can be done the same way by doing borrowing and subtracting. Works the same way. Or, as I described to you, taking the negative of that number that you want to subtract and adding it to the number, the first number that you're subtracting from. And I described the 2's complement, and it's written down as like that, 2's complement, or sometimes TWOS complement. And you simply reverse the bits. So all the 0's become 1's and all the 1's become 0's, and then you do a simple addition of 1. You can do all the carrying through if you need to, and that's how you make a 2's complement, or the negative of a number. So there's positive 67, this is decimal, and here's what negative 67 looks like. What else did I talk about here? Oh yeah, I talked about the sign bit. Here's positive 67. The sign bit is the leftmost bit, and it's only the 1 bit. It's not any more bits. It's just the upper bit, and it's no matter how big the number that it is, how many bytes it is, or how many bits the number is, the upper bit is always considered the sign bit when you're dealing with sign numbers. And you have to specify that when you when you write your code, because the compiler will treat signed numbers differently than unsigned numbers. And so negative number, the upper bit, the leftmost bit, is a 1 if the number is negative, and a 0 if the number is positive. And we talked a little bit more about, oh yeah, this sign extension when you're casting from a smaller number to a bigger number, and how the sign bit, the upper bit, gets cast through the upper portions of the new bigger number that you're casting the smaller number to. So if you're casting a byte to an int, then the sign bit will be projected through the whole upper part of the logical operators, and, or, exclusive or, and complement. I talked about complement already. You just change all the 1's to 0's and all the 0's to 1's. The AND operator just means that anywhere there's a 0, your result will be a 0. In order to get a 1, both the bits that you're ANDing together have to be 1. The OR operator is anywhere there's a 1 bit, you'll get a 1 out as a result. In order to get a 0, both the bits have to be 0. The exclusive OR is a bit weird. It looks like an OR, but you have a 0 here as well. So what it means is if the two inputs are different, either one's a 0 and one's a 1, then your result will be a 1. If they're the same, the result will be 0. So if they're both 0 or both 1, you will get a 0 output. And I showed you how to manipulate an individual bit and a byte, or on in this case, say the I/O port on the microcontroller, port D, and how you can manipulate a single bit. You can change the sign of it. You can clear it or set it or toggle it using the exclusive OR. So if you want to clear a bit on a port, you use the AND operator and put in zeros where you want those bits to be cleared. If you want a bit to be set on a port or in a byte, you make that bit that you want to set 1 and OR, and use the OR operator. And finally, we looked at combining different operators, or actually I kind of glossed over the shift operator, but I went through it in a little bit more detail the second time around. That's the shift operator, and it requires a number after it, and that just tells you the number of bits that you're shifting, either shifting left or shifting right in this case. So this was a very complex tutorial on binary numbers. It's something you got to play around with and experiment with and just learn how to understand and recognize and identify the different types of things you can do with binary numbers. The computer does that, or the microcontroller does that automatically on its own, because that's the language, that's the number system it works in. We're used to a decimal numbering system, which looks different, but it operates the same way. And I will put in some links to some information on binary numbers. Wikipedia has got a couple of good articles on binary numbers, and there's a little bit on the Arduino reference part of the website as well that talks about binary numbers and the different shift operators and the ANDing and the ORing. So I hope this video was useful for you. I hope you got something out of it, and stick around. I've got a few more on the way. Hopefully you'll stick around and watch a few more. Thanks for watching. See you next time.